Okay, say you've got a chemical system like this cylinder filled with water vapor, and it's sitting at equilibrium. The pressure inside the cylinder is equal to the external pressure, and so there's no net force acting on the lid. The water vapor is just sitting here, minding its own business in the cylinder. And now, say that we apply some heat to this. So maybe this is a piston in a steam engine or something. The heat flows into the system, makes the molecules move faster, and causes the water vapor to expand. In expanding, the water vapor pushes back the surroundings. And so the heat is flowing into the system, and the system is doing work on the surroundings. So what's happening here is most of the energy that's flowing in as heat is going into raising the energy of those water molecules, but some of that heat energy is going right back out in the form of work to push back the surroundings. And this is a very common situation. Moreover, just by existing and taking up space, a system imposes work on the surroundings. So, in addition to the internal energy in a system, the space that the system takes up has effectively pushed back the surroundings, and so has added an energy equal to PV in the surroundings. And so, for a process that's occurring at a constant pressure, the any heat that's flowing into or out of the system is going to go into both changing the internal energy of the system and changing the this PV part of the energy of the surroundings. So if the system expands, then the surroundings will be gaining energy because work is being done on them. If the system shrinks, then the surroundings are doing work, and so they're losing energy. But the heat is going into both of these places. And so for a constant pressure process, the amount of heat that's involved, QP, and the subscript P here just indicates that this is happening at a constant pressure. That heat is equal to the change in this total, the change in U plus PV. This kind of a situation where you've got a process happening at a constant pressure, where the system is free to expand or contract as its volume changes, is very common, and so the heat that's associated with such a process is going to be associated with this change in the total of internal energy plus pressure times volume. And so, since this is such a common situation, this combination here, this U plus PV, is a very useful quantity. And so you can think of it as, it represents the internal energy of the system plus some part of the external energy that's just due to the fact that the system takes up space. And it's this total that changes in response to heat at constant pressure. So this total is a very useful quantity, and it's given a name. It's called enthalpy with the symbol H. Enthalpy is the word comes from a Greek root meaning warmth, and so its name basically ties into this idea that the heat involved in a process is equal to the change in this enthalpy quantity. And so specifically, the heat at constant pressure is equal to the change in the enthalpy of a system. And I want to emphasize here that the pressure and the volume in this PV, those are both properties of the system. So we're talking about the pressure of the system, the volume of the system, and when we're in these conditions, the pressure of the system is perfectly balancing the pressure of the surroundings. And so this PV represents energy that the system is causing in the surroundings, but we can relate it to properties of the system. So U plus PV is all based on properties of the system, and so U plus PV itself is a property of the system. Enthalpy is a property of the system, and changes in enthalpy are equal to the amount of heat that's involved for a process that's occurring at a constant pressure. Now there is a caveat here. This equality that the heat is equal to change in enthalpy only applies if there isn't any other work going on. So if the system were doing other kinds of work, say it were driving an electric current, or if it were being used to compress a spring or do some other kind of work, then there would be other things affecting the energy. But if the only things affecting the energy are the internal motions and arrangements of the molecules, along with the compression of the surroundings, under those conditions, then the heat is going to be equal to the change in this enthalpy quantity. And the letter H is used, well, that refers to heat. So enthalpy is closely related to the heat involved in a process, and so the symbol H reflects that. So these processes happening at constant pressure are very common. So this shows up all the time in processes that occur in the laboratory, shows up all the time for processes that occur in nature. And so this enthalpy is a highly relevant quantity if we're talking about studying chemical systems, whether it's in a laboratory environment or in an environment in nature. And now the good news is enthalpy is, under most conditions, enthalpy and internal energy are very close to each other. They're very similar in magnitude. And just to illustrate that, I want to talk about the enthalpy of 1 mole of liquid water. 1 mole of water has a mass of 18 grams, and so if it's a liquid, it would have a volume of 18 milliliters. And if this beaker is just sitting out in atmospheric pressure, standard atmospheric pressure it is equal to, it's 1 atmosphere. In metric units, the standard pressure is 101,325 pascals. And so PV, pressure times volume, of this mole of water is going to be 101,325 pascals times 18.0 milliliters for 1 mole of water. And Pascal is the metric unit, it's the SI unit for pressure, and it is equivalent to a joule per cubic meter. And then a milliliter is a cubic centimeter, and since a centimeter is 1/100th of a meter, a cubic centimeter is 1/100th cubed of a cubic meter. So a milliliter works out to be 1/1,000,000th of a cubic meter. And so if we multiply this out, 101,325 joules per cubic meter times 18.0 times 10 to the minus 6 cubic meters, the PV term in the enthalpy here is 1.82 joules per mole. And that's a pretty small amount of energy. Joule is a unit of energy, and if you the amount of heat that's involved, if you were to add 1.82 joules of heat to this water, it would raise the temperature by only 0.0242 degrees Celsius. So the difference between enthalpy and internal energy is pretty small, and so you'll often see the terms enthalpy and internal energy. You'll often encounter them being used almost interchangeably, and that's I guess that's understandable. They are very similar in concept, and they're also close to each other in magnitude. They are different ideas, and so do try to keep them straight, but really you can't be faulted for at least colloquially saying that enthalpy is basically a lot like internal energy. So I wanted to show you an example of applying this enthalpy idea to an actual experimental measurement. And so I'm going to go back to a situation that I described in an earlier video where we're making a saturated solution of sodium chloride by dissolving 29.2 grams of sodium chloride in 100 milliliters of water. As the sodium chloride dissolved, the temperature of the solution fell from 22.3 degrees Celsius to 17.8 degrees Celsius. And then, assuming that the heat capacity of the solution is 3.30 joules per gram degree Celsius, this time we want to determine the enthalpy change of this dissolution per mole of sodium chloride. So we want to find the enthalpy change. And since this process is occurring at constant pressure, the system we're not constraining the solution in a confined volume. It's free to expand or contract as needed as the process is occurring. So this is a constant pressure process, and there's no other work being done. So the heat associated with this process is going to be equal to the enthalpy change. And then to find that heat, you make use of the temperature change of the solution here. The heat is equal to the negative of the heat capacity, or the specific heat of the solution, times the mass of the solution in grams times the change in temperature. And the negative sign here reflects the fact that the heat is flowing out of the solution. The solution's getting colder, and the heat is flowing into the sodium chloride. So the heat flowing into the NaCl is equal and opposite to the heat that is flowing out of the water. So that's why that minus sign is there. And so if we put in the heat capacity of the solution, and that was given in the problem, the total mass of the solution, which is equal to 129.2 grams, and the temperature change, which was negative 4.6 degrees Celsius, we find that the heat here, the heat that's flowing into the NaCl, is a positive quantity. It's positive 1,918.62 joules. And then to express this per mole of NaCl, we just need to convert the mass of the NaCl, 29.2 grams, multiply that by the conversion factor. 1 mole of NaCl has a mass of 58.35 grams. And so we find that we've got just over half a mole of NaCl. So the enthalpy change, the delta H of the NaCl, is the heat, positive 1,918.62 joules, divided by the number of moles, 0.500428 moles. And so that's equal to positive 3,833.96 joules per mole. And then finally, we want to round this off to 2 significant figures of precision because our temperature change only had 2 significant figures. And so our delta H is positive 3.8 kilojoules per mole. And I'm including the positive sign just to emphasize that the enthalpy of the sodium chloride is increasing during the dissolution process. So heat is flowing out of the solution and into the NaCl. The NaCl is gaining enthalpy. This is an endothermic process. Enthalpy is increasing. Heat is flowing into the chemical system of NaCl.